So I want to give you a taste of how quadratic functions or quadratic equations are used in the real world. They were developed for a reason, and people really got going with these things in the 17th century, um, especially studying the science of ballistics or how things objects flying through the air being affected by gravity, basically. So here I found this old school illustration of a cannon and the various trajectories that the cannonballs would take given whatever angle you shoot it at. Sorry, this is kind of a violent lesson, but this is I don't know. This is for the people who like to shoot stuff and blow stuff up, um, or think about such things. It's cool. I don't know. Projectile motion is pretty cool, and it's all it's this is where um, the quadratic functions really started taking off in mathematics. Well, pun not intended, but should have been intended. Um, yes. So the equation that describes the height of a projectile, a cannonball, let's say, um, as a function of time, you shoot it, and then as time goes on, it reaches a certain height and then starts falling back down. That that equation that um, shows you that is this. Um, it's it's a quadratic. It's a quadratic equation. Um, Delta y, change in y, meaning it's um, displacement from the ground. If you consider the ground your starting point, its height basically is equal to 1/2 times g, which stands for the acceleration due to gravity, which is roughly um, negative 10 meters per second squared, or 10 meters per second per second. And I'm going to call it negative because it goes in this direction. We'll call this direction positive. Um, so 1/2 g times t squared. T is time. So however much time has passed in seconds, square that, plus vy initial, um, the velocity in the y direction or up. It's vertical velocity, I like initial, like its initial vertical. So this means its initial vertical speed, it's vertical velocity, plus um, the displacement of y at the beginning. Where you start. If you start at the ground, that would be 0. If you start off the ground, you're on a little hill or something. Its displacement is the height of the hill. So the distance relative to what you're considering 0 or ground level. Okay. So here I've got a little setup here. The acceleration due to gravity is constant near the surface of the Earth, so that just is what it is, negative 10 meters per second squared. Which means every second you're accelerating by 10 meters per second downward in this direction. Your initial velocity is 30 meters per second, and your initial height is 5 meters. So let's write the equation for that based on this basic outline. So my displacement delta y, I could just call that y for simplicity. Y equals, actually let's call it height. Let's just h for height. Height equals 1/2. Now g is negative 10 meters per second um, times time squared. Time squared. So I'm just gonna call that t. This is gonna be a function of t. So we'll be able to plug in any time, like 2 seconds, 3 seconds, 4 seconds, time squared, plus my initial velocity, which is 30 meters per second times time, plus my initial height. So however far up I started. In this case, I'm just arbitrarily saying, let's pretend we're on a hill that's 5 meters high. So we're going to say plus 5 meters. Or maybe the top of the cannon is 5 meters off the ground or something. It's a big guy. plus 5. Okay, so if you look at this, actually let me just do this out. 1/2 times negative 10 would just be negative 5. So we got negative 5 t squared plus 30 t plus 5. If you look at that, that should look familiar, right? That's a quadratic function. F of x, the output of the function is equal to ax squared plus bx plus c. A here is negative 5, b is 30, c is 5. Okay? So, okay, well, why would we want to solve this quadratic function? Why would, and solving means finding the roots, or finding where that parabola crosses the x-axis, which in this case is the ground level. We're considering that ground level at y equals 0. Y equals 0 meters. You're 0 meters off the ground. Why would we want to solve that? Well, what happens when it crosses the x-axis over here? This explosion is a little clue. That's where the cannonball reaches the ground after you shoot it. So you'd want to solve that because you'd want to know where the cannonball would land. And this is actually, this is very functional if you're a general or something, and you need to know where to aim stuff, right? I mean, this is actually, this is a real live use of a quadratic function. This is in large part why these things were developed. And if you're, if the violence aspect of this is troublesome, imagine you're launching, like a stuffed teddy bear over to a friend who's going to catch it and thank you for it. Okay, but I'm going to stick to cannonballs. Okay, so we want to solve this. We want to know, when does it hit the ground? It's going to hit the ground at one of its solutions, at one of its roots. Now, I can ignore this root because this is in negative time, right? It's some kind of x equals negative something. Well, in this situation, negative time doesn't mean anything. I'm talking about shooting a cannonball and then it hitting the ground later. I'm not talking about shooting the cannonball and then realizing in some parallel universe back in time, it was on the ground theoretically, So I'm going to ignore that solution. Okay, so I'd want to solve this. One way to solve it is to factor. There's the factor method. I'm trying to think if I could do that easily. Probably not. Take too much time right now. Where you set that equal to 0 and factor, and then set each one to 0 and find out the different values of t. Another way is just to graph it and then find out where it crosses. So I happen to know that that point is I think it's 6.16 seconds roughly, something like that. The reason why it's not 6 exactly is because we started off the ground a little bit. I just did that to show you what you would do with this. All right, 6.16 something seconds is where it hits the ground, and then this is like negative 0.16 something. So you can graph it, find the root, find the roots. This is the only root that makes sense in the context of a real life problem. A negative time doesn't, from the beginning doesn't really mean anything. So what would you do with this? You'd say, okay, well, based on this equation, I know it's going to hit the ground in 6.16 seconds. All right. Now, but how far does it go? I mean, what is the distance it would go? This axis doesn't represent distance. It represents time in seconds. So I know it hits the ground after 6.16 seconds, but I don't know yet how far it actually go horizontally before it hits the ground. I know it'll go. From here I can see where it'll go vertically. I can look at the maximum of the parabola, the vertex, and it's somewhere around 50 meters. So the cannonball goes vertically 50 meters up and then back down. But where does it go horizontally in that time? So I can take this 6.16 seconds and actually plug it into another equation, which tells me, so distance equals speed times time, right? So that's basically what this is saying. Your displacement in the horizontal direction is equal to your initial velocity times the time at which you're traveling that velocity. You know, so if you drive 50 miles an hour for 2 hours, you're going to drive 100 miles, right? So that's the setup here. So I could do delta x, or its displacement or distance traveled, is my initial velocity in the x direction. Here is my initial velocity in the y direction. You know, going up at 30 meters per second. Basically, it'd be like this. I'm actually shooting the cannonball at an angle like this, right? Well, there's two components to that velocity. There's the velocity in the x direction, and there's the velocity in the y direction. So I could actually turn that into, you don't, I mean, you can kind of ignore this, but turn that into a right triangle, and I could split up this thing into its vertical and horizontal components with sine and cosine and stuff like that. Anyway, I'm just telling you what the vertical velocity is. So the horizontal velocity, the x velocity, is 40 meters per second. So I would just take this. So it's going horizontally. It's going 40 meters per second. For how long before it hits the ground? 6.16 seconds. That's the solution to that quadratic function. 6 times 6.16. So I'm going to ignore the 0.16. So it'd be roughly 240 meters. So it'd go horizontally about 240 meters before it hit the ground. So you can see, I mean, it's a practical value. If you're trying to aim and hit something and blow it up, you want it, and you can figure out what the angle of your shot is, and then the initial velocity. Then you find out the vertical velocity and horizontal velocity. You use these equations, one of which is a quadratic one, to figure out how long it goes before it hits the ground, and then use that information to figure out how far it goes before it hits the ground in the horizontal direction. All right, good luck. Don't really shoot anything that would hurt anyone. But you can try this with, like, they have those trebuchet building contests, or where you shoot pumpkins or something. Anyway, good stuff. Projectile motion.